here is the derivation of this line integral of a vector field formula. So basically we have this line integral of f over a curve C. Now in this case our f is a vector field. So what we did was we consider the tangential component of vector field along this curve C, and so basically this ds vector becomes tangent vector times ds. Now notice this ds is a scalar quantity. Now from chapter 10 we know that unit tangent vector t equals to c prime t over its magnitude. So then instead of t I can substitute c prime t over its magnitude. Now what is ds? ds is the arc length element, now which equals to magnitude of c prime t dt. Next what we can do is we can cancel the magnitude of c prime t from the numerator and the denominator, and if you do that you will get the line integral of vector field f ds f dot ds over the curve C equals to the formula that we defined earlier. Okay, next I want to talk about a specific form that we used in line integrals. This form is called the differential form. This is just a notation. Let's say we have a vector field f with three components f1, f2 and f3, and we are given a curve C of t with parameterization x of t, y of t and c of t. Then we know that according to the definition this line integral equals to line integral of f dot c prime t. Now what is f? F is f1, f2 and f3 vector. And what is c prime? C prime is, since c of t equals to this, its derivative should be x prime t, y prime t and c prime t dt. Now let's take this dot product. You have f1 times x prime t plus f2 times y prime t plus f3 times c prime t dt. However, x prime t is the same as dx over dt. Y prime is dy over dt. C prime is dc over dt. Okay. Now you can think these three quantities dx over dt and dy over dt and dc over dt as a fraction. Mathematically it's not correct, but let's think like that. Then what we can do is we can cancel this dt terms with this one, and after that we will get a form called the differential form of a line integral. Sometimes in problems we are given this line integral. In a case like this, what you need to do is you need to think. So simply consider this form. Then we can do the integral. Okay, so let's consider an example from this. Say this is example 13.2. I think this is the fifth one. Let's say evaluate the line integral x squared dx plus xy dy plus yc dc, where c of t equals to t comma t squared comma t cubed. For 0 less than or equals to t less than or equals to 1. Okay, so basically now we know that this differential form can be written in the following way. So we have x squared x squared dx over dt plus xy times dy over dt plus yc times dc over dt times dt, and t goes from 0 to 1. Okay, now what are x, y and c? Well, according to the curve, your x coordinate is t, y coordinate is t squared, and c coordinate is t cubed. Okay, so now this integral becomes x coordinate is t, therefore x squared should be t squared. What is dx over dt? Dx over dt, which is the derivative of x with respect to the t variable, is 1 plus x is t, y is t squared. And what is dy over dt? Dy over dt is 2t plus y coordinate is t squared and c is t cubed. Dc over dt equals to 3t squared. Now we have dt. Now let's simplify the integrand. So we have t squared plus 2t to the power 4. T times t squared is t cubed. T cubed times this t becomes t to the power 4, and we have 2 plus 3 times t squared times t cube is t to the power 5. T to the power 5 times t squared is t to the power 7. Okay, now let's integrate this. We have t cubed over 3 plus 2 t to the power 5 over 5 plus 3 t to the power 8 over 8. Let's apply the limits. Lower limit is 0, upper limit is 1. Okay, let's evaluate the upper limit first. You will get 1/3 plus 2/5 plus 3/8 minus 0, and the answer should be 1/3 plus 2/5 plus 3/8.